Have you ever wondered what happens when a star, one of the massive celestial objects illuminating the night sky, dies and ends its life cycle? The story of a dead star is not just about an ending, but about the universe's journey of transformation and rebirth. The lights twinkling in the night sky are powerful reminders of the vibrant and intense cycles of the universe. Today, let's delve into this fascinating journey and understand why the death of a star is so significant. 1. The life cycle of a star from cosmic dust to radiance. A star doesn't appear out of nowhere. It begins its journey in vast clouds of gas and dust known as nebulae. Gravity pulls particles closer together, creating dense clouds. When pressure and temperature become high enough, nuclear fusion reactions ignite, and the star is born. The Eagle Nebula, with its famous Pillars of Creation image captured by the Hubble Space Telescope, is a striking example of star formation. After its birth, the star enters the main sequence phase. This is the most stable and prolonged period of its life, during which stars like the Sun continuously generate energy through nuclear fusion. The light emitted by stars not only brightens the sky, but also provides essential energy for sustaining life on surrounding planets. The Sun, which has existed for approximately 4.6 billion years, exemplifies the critical role stars play in supporting life. However, nothing lasts forever. As the fuel in a star's core runs out, it moves into the final stages of its life, a journey filled with dramatic changes. 2. The collapse of massive stars, the spectacle of supernova. For smaller or medium-sized stars, they expand into red giants before shedding their outer layers and leaving behind white dwarf remnants. But for massive stars, the end of their life is far more intense and spectacular. When the core of a massive star can no longer sustain nuclear fusion, it collapses under the weight of its own gravity. This triggers a supernova explosion, one of the most powerful phenomena in the universe. This explosion not only releases an enormous amount of energy, but also creates heavy elements like gold, uranium, and silver, which are essential for life. A well-known example is the supernova SEN 1987A, observed in the Large Magellanic Cloud in 1987. This event provided valuable insights into the death of massive stars and their contributions to the universe. 3. The remnants of stars, neutron stars, and black holes. After a supernova, the core of a star may become a neutron star or a black hole, two of the most extraordinary objects in the universe. Neutron stars are small, yet incredibly dense celestial objects. Despite being only 10-20 kilometers in diameter, they can have a mass 1.4 to 2 times that of the Sun. Their density is so extreme that a teaspoon of neutron star material would weigh billions of tons. Neutron stars often spin rapidly, emitting regular pulses of radiation known as pulsars. A prime example is the pulsar in the Crab Nebula, spinning 30 times per second and emitting powerful energy in X-rays and radio waves. Black holes, on the other hand, are regions of space where gravity is so strong that nothing, not even light, can escape. In 2019, the Event Horizon Telescope captured the first ever image of a black hole's shadow, confirming Einstein's theory of general relativity. Black holes are not just the endpoints of matter, but also factories of immense energy, playing a key role in shaping surrounding galaxies. 4. The significance of star death rebirth in the universe. The death of a star is a transformative event in the universe. While it signifies the end of a star's life, it also heralds the beginning of something extraordinary. The elements forged within a star's core during its life and those created in the fiery aftermath of a supernova explosion become the seeds for future celestial bodies, planets, and even life itself. Let's explore this profound process in greater depth, supported by scientific evidence and examples. When a massive star dies in a supernova explosion, its core collapses under immense gravitational pressure, reaching temperatures of billions of degrees. This intense environment allows nuclear fusion to produce heavier elements that could not form during the star's stable lifetime. Elements such as iron, gold, silver, uranium, and even rare isotopes are created in these moments of cosmic violence. For example, the radioactive element technetium, which has no stable isotopes, was discovered in the spectral lines of red giant stars. This finding confirmed that heavy elements could only form under extreme conditions like those found in supernova. The solar system, a product of star death. Your solar system itself owes its existence to ancient stars that lived and died billions of years ago. Evidence from isotopic analysis of meteorites, such as the famous Allende meteorite, reveals the presence of elements like aluminum-26 and calcium-41, which are products of supernova. These short-lived radioactive isotopes could only have been introduced to the young solar system by a nearby supernova explosion, which enriched the primordial gas cloud that eventually collapsed to form the Sun and its planets. Furthermore, the isotopic composition of oxygen and other elements in Earth's crust matches the predicted ratios found in supernova ejecta. This provides direct evidence that the materials forming Earth, and by extension, all life on it, originated from stardust. The connection between stardust and life. As Carl Sagan poetically stated, "We are made of star stuff." This sentiment is supported by science. The fundamental building blocks of life, carbon, nitrogen, oxygen, and other essential elements, were all synthesized in stars and scattered throughout the cosmos by supernova and stellar winds. For example, the iron in our blood, critical for transporting oxygen, was forged in the heart of a star. The calcium in our bones, providing structure and strength, and even the hydrogen in the water we drink, which originated from the Big Bang, all have cosmic origins. Without the death of previous generations of stars, the elements necessary for life would not exist. Supernova and star formation. Supernova explosions are not merely destructive. They play a crucial role in the ongoing cycle of star formation. When a star explodes, the shock waves it generates travel outward, compressing nearby gas clouds and triggering their collapse. This process is essential for the birth of new stars and planetary systems. For example, the Orion Nebula, a well-studied stellar nursery, shows signs of star formation initiated by the shock waves from nearby supernova. Observations using the Hubble Space Telescope have revealed dense gas clumps in the nebula, potential sites for new star formation shaped by these cosmic events. Another example is the supernova remnant Sen 1572, also known as Tycho's supernova, observed by Tycho Brahe in 1572. This remnant continues to interact with interstellar gas, creating regions of high density that could lead to future star formation. The cycle of galactic renewal. The death of stars contributes to the perpetual renewal of galaxies. Supernova distribute metals and energy throughout their host galaxies, enriching the interstellar medium and driving the processes that sustain galactic ecosystems. Without supernova, galaxies would become inert, as the necessary ingredients for star formation and planetary development would be locked away in aging stars. Studies of the Milky Way's galactic disk show that it has been continually enriched over billions of years by supernova, creating a metallicity gradient that reflects this process. Observations of older, metal-poor stars in the galactic halo, compared to younger, metal-rich stars in the disk, further support the idea that star death is integral to galactic evolution. The connection between stardust and human biology is further supported by isotopic studies of elements in our bodies. For example, 1. The ratio of carbon-12 to carbon-13 in organic molecules aligns with those produced in red giant stars. 2. Oxygen isotopes in biological systems match those observed in interstellar dust clouds. This evidence underscores the universality of the materials that make up both living organisms and celestial bodies. Conclusion: a cycle without end. The death of a star is not the end of a story, but the beginning of countless new ones. Every element scattered by supernova enriches the universe, forming the building blocks for new stars, planets, and the potential for life. This ongoing cycle of creation and destruction ensures that galaxies remain dynamic and evolving, a constant interplay of death and rebirth. As we look up at the stars, we are not just gazing at distant lights, but at the origin of everything we know. Each atom within us carries the legacy of a star that died billions of years ago, reminding us of our profound connection to the cosmos. The story of a dead star is a vivid testament to the wonders of the universe and its perpetual cycles. Understanding the life and death of stars not only unravels the universe's greatest mysteries, but also reveals our own origins. Each of us is part of this magnificent story, intricately connected to the vast and awe-inspiring cosmos. If you find this story fascinating and meaningful, share it with your friends and loved ones. Spread this knowledge so more people can realize that even though we are small in the universe, we are deeply connected to it. Don't forget to explore other topics about astronomy, as the universe is full of incredible stories waiting to be uncovered.